in section 311, we actually get to one of the main points of this semester, where we're going to write and balance chemical equations. So this is a high point here. This is exciting. What is a chemical equation? Well, we've been talking about them and showing them and kind of pretending like you already know what they are all the way through, and you probably do because I'm sure you've seen something like this in high school, but chemical equations are the shorthand way to show some sort of chemical change. So if I say that, or observe that, dissolved silver ions and dissolved chloride ions form silver chloride, then what I'm saying is Ag plus, which is a silver ion, dissolved, so we'll say aqueous, plus dissolved chloride ions, so Cl minus, which are dissolved, so we'll say aqueous, goes to make silver chloride solid. Okay. So what do all these symbols, lines, dashes, etc. mean? Well, there's three ways that we can list things in a chemical equation. We can give you the reactants, which are the initial components, and those will be on the left side of this arrow. Okay. So in our previous example, the silver ions and the chloride ions are the reactants. We draw in a plus just to show we're going to write in a new compound. So silver plus ion plus chloride ion, so it means this is also present and hopefully reacting with the other components. But everything on the left side of the arrow called reactants. Then we can have the products, that's what we're making as part of this reaction. Those will be on the right side of the reaction arrow. So in this case, silver chloride solid is our only product, but if we had more, we would just write plus and write the additional products there. And then we're going to want to give the state of matter for each compound if we know it. Sometimes we leave it out if it's not critical to understanding what we're talking about, but we do this in parentheses, a single letter or two letters, and as a subscript. S for solid, L for liquid, G for gas, and AQ for aqueous, which means that it's dissolved in dissociated ions of that substance in water. So here we're saying the silver plus ions are dissolved dissociated ions in water, and so are the chloride ions, and the silver chloride material is a solid. And then the critical aspect, we have the arrow, which says that we are changing from reactants into products. So let's look at this again. Let's see, a lump of carbon burns in the presence of oxygen to form carbon dioxide. So we translate. Carbon, it's a lump, so we're going to say it's solid. Oxygen is diatomic, when it's by itself in the air. We know that because it's one of the 7 chemicals, or 7 elements that are diatomic. Those are hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. Okay, those are the 7 that occur naturally as diatomic molecules. Oxygen, we're assuming this is at room temperature, so we'll say it's a gas. Forms carbon dioxide. We know how to translate that into a formula, and it's a gas. It's carbon dioxide at room temperature is a gas. Pretty straightforward. Calcium metal. Okay, so calcium metal. Metals are solid unless they say otherwise. Reacts with chlorine gas, diatomic again. Cl2 gas to produce aqueous calcium chloride. So to produce tells us that's what it's making. Just like to form says arrow, that's what it's making. Aqueous calcium chloride. Now the Cl, the 2 here is not from the 2 over here. We've reevaluated and said +2 and -1 for chlorine, +2 for calcium. Calcium chloride, translating the name to the compound, requires a second chlorine to balance the calcium. Now, getting to that point, we still have to obey all the laws that we talked about before. And with reactions, the main one that we have to think about is the conservation of mass, that what we start with is what we end with. And while that was an observation of mass, we know now from Dalton's atomic theory that everything's made up of atoms, and the reason conservation of mass works is the atoms are only rearranging. We don't get new atoms, we don't lose any atoms. So if we say something like silver metal reacts with chloride gas, there we go, chloride gas, to give us silver chloride solid, AgCl, +1 for silver, -1 for chlorine, so that's balanced already, and that's it. We have an issue here. I have 2 chlorines on the reactant side, but only one of them seems to be on the product side. So it's like one chlorine has disappeared, which violates the conservation of mass law. So in order to fix this, what we have to do is we have to put coefficients, that's a number in front of whatever particular compound we're dealing with, in order to make more of those be present in that reaction. So we'll say that maybe there's 2 silvers in this reaction, and 2 chlorines in the form of 1 chloride molecule. And that makes 2 silver chloride. Well, 2 silvers, 2 chlorines. If we say there's 2 of this whole unit, silver chloride, then now all of a sudden everything is okay again. The universe can go on about its business. I have 2 silver atoms, 2 chlorine atoms hooked together, bonds rearrange, and now silvers and chlorides are attached to each other. But I have 2 silver chlorides attached to each other, so 2 silvers and 2 chlorines before and after the chemical reaction has occurred. So how do I do that? I figure out how many atoms of each element are present. I use coefficients to indicate multiple entire molecules. So the 2 in front of the silver chloride meant I have a silver chloride and I have a second silver chloride. That's what that means. Then we keep checking the count of atoms until everything is equal on both sides. Let's try that. Let's see, we have C3H8 propane with oxygen burning to make carbon dioxide and water vapor, or actually liquid water here. We're going to kind of divide the 2 halves here between the reactants and the products and start counting atoms. 3 carbons, 8 hydrogens, 2 oxygens. Okay? 1 carbon, 1, 2, 3 oxygens, and 2 hydrogens. Alright, so not much is balanced. In fact, nothing is. So how do we get from 3 to 1? What can we add? Well, we can add a 3 in front of carbon dioxide. That will change the number of carbons to 3. But notice it also changes the number of oxygens. Now I have 3 times 2 is 6, plus 1 is 7. So we're keeping a running tally here of how many of these things we have on each side. Alright, carbon's at least okay now. Let's look at hydrogen. I have 8 and 2. So if I put a 4 here, now I have 4 times 2, I have 8 hydrogens on both sides. Excellent. 8 hydrogens, 8 hydrogens, 3 carbons, 3 carbons. 3 times 2 is 6 oxygens, plus 4 times 1 is 10 oxygens altogether over here. Okay, so we see that 3 times 2 is 6 oxygens. 4 times 1 is 4, so 6 and 4 is 10. Alright, 10, we only started with 2, so what I have to do here is add some more oxygen on the reactant side. Say there's 5 O2 molecules, So 5 times the 2 gives me 10 oxygens. So 3 carbons, 8 hydrogens, and 10 oxygens. Excellent. This is balanced. So this is the ratio of propanes to 5 oxygens. So I need 5 oxygen molecules for every propane. And when every propane burns, I get 3 carbon dioxide molecules. Every 5 oxygens I use up, I make 4 waters, etc. I can make any ratios I want here using this equation. And I can use these as conversion factors, which we will later on. And I can use any two of them just by putting the numbers in front of them. I can use them in any direction. Okay. Let's try a more complicated one. Doesn't look more complicated, does it? We have ethene, oxygen, and making carbon dioxide and water again. Let's try our same strategy. 2 carbons, 6 hydrogens, 2 oxygens, 1 carbon, 2 hydrogens, and 3 oxygens. All right, we've played this game before, right? There's 2 there, and now we have more carbon. Now we have 4 plus 1 is 5 oxygens. On this side, 2 times 2 is 4, plus 1 is 5. So we have 6 hydrogens over here. So we're going to need some more over there. So let's say 3 here, and that gets 3 times 2 is 6. Excellent. But now we've added 3 more oxygens, so 2 times 2 is 4, plus 3 is 7. Uh-oh. There's no good way to get from here to there, is there? So when this happens, you have 2 choices. The direct way is to say, well, I guess if I had 3.5 of these, that would work. And now everything would be happy and balanced. I can't have 3.5. So what I'd have to do is go back and double everything so I have whole number ratios. So 2, 7, 4, and 6. So at that point I have 4 carbons, 12 hydrogens, and 14 oxygens. Here I have 8 carbons. No, I'm sorry. 4 carbons. I have 6 times 2 are 12 hydrogens. And 6 plus 8, I have 14 oxygens. It's balanced. All right, well, what if I didn't want to work with fractions? Erase some of this stuff. Heck with it. Erase everything off the slide. All right, so where were we? We had said 2 of these and 3 of these, which gave us 2 carbons, 6 hydrogens, and 2 oxygens. 2 carbons, 6 hydrogens, and 7 oxygens. Okay, so this is where we were when we decided to try that 3.5 craziness. If you get to this step, what you can do is look for the most complicated molecule and double it. And just say, all right, heck with this. I'm going to say there's twice as many of these and see if that works any better for me. Okay. So 4, 12, and still 2 oxygens. All right, so now I have to reevaluate this side. 2 doesn't work anymore, so I'll put a 4. 3 doesn't work anymore. I need 12 hydrogens, so I'll put a 6. Good. 4 times 2 is 8 oxygens. 6 times 1 is 6 oxygens. That's 14 oxygens. So what do I need here? I need a 7. and now it's balanced. There's a certain element of trial and error with these sort of calculations, these sort of processes. There's no perfect way to do this. I mean, we try to go with the most complicated molecules and balance the elements in that one first, leave things that are elements by themselves until the end, because it's going to adjust the least amount of things to put a number in front of it, so it's a good thing to try and throw a number in front of it at the end. But for the most part, you're just kind of winging it and keeping track of the atoms and hoping you can figure out the right ratio by the time you're done. The good thing about this for exams is if I give you enough time, you can figure this out by randomly guessing numbers if you really had to, right? I mean, you could just keep putting numbers in and keep adding up the number of atoms on each side until eventually you got a set of numbers that worked. Or you could try it, say, nope, that didn't work, try it again, nope, that didn't work, try it, hey, it worked. That was the simplest whole number ratio, and it works. I have the same number of atoms on each side, so it's balanced. So no matter what, you know when you're right when you're doing something like this, because the number of atoms are the same on both sides. So these are great to have on tests because there's the kind of problem that you know you get right or you know you don't have right, and you keep trying that. Well, what if we have polyatomic stuff present? That kind of adds a lot of atoms. Well, one trick is, if you have something polyatomic that stays the same and altogether the same on both sides, then you can say, I'm just going to pretend this is one unit. So what I would say on this side is that I have one calcium, two chlorides, one silver, and one nitrate. On this side, I have one calcium, one chloride, one silver, and two nitrates. Now, does this mean that if you had just broken this down into 2 nitrogens and 6 oxygens and 1 nitrogen and 3 oxygens that it wouldn't be able to balance? No, you could figure it out. It's just a little bit faster if the polyatomics stay as the same polyatomic on both sides of the arrow. It's just a little faster to balance them as a unit. Alright, so let's look at this. 1 calcium, so far so good. 2 chlorines and 1 chlorine. That's not going to fly. Alright, so we're going to need more chloride over here. So I put a 2. Well, that's going to give me 2 chlorines, but it also gives me 2 silvers. So now 1 silver to 2 silvers. I only have 1 silver here, so I got to up the ante a little bit there. Now I have 2 silvers, but now I've added another nitrate, so 2 nitrates. Look, perfect. It balanced itself at the end. That's not as rare as you may think. A lot of times you'll get that to happen where the last group or last element that you leave to balance balances itself. Yeah, so if you're looking at one of these problems and you see, for instance, say oxygen everywhere, it's just oxygen in every compound, don't balance oxygen first. Leave it till the end, because if it's everywhere, anything you do is going to switch the amount of oxygen anyway, so you're going to have to readjust it all the time. And secondly, if you're lucky, it'll balance itself at the end, like a lot of times they do. You won't have to deal with the most complicated one there. Alright, let's try one more and then say that we're experts at this and can go try 100 or so in the homework. Strontium chloride goes to lithium plus lithium phosphate, turns into strontium phosphate plus lithium chloride. Alright, sure the charges change, but we're not going to get real hung up on that here. We're just going to kind of push through this and see what we get. 1 strontium, 2 chlorines, 3 lithiums, and let's see, polyatomic stays together, so we're going to say 1 phosphate. So that PO4 with a 3 minus charge. I'm not really including the charges here. They're going to neutralize out since everything's neutral, so we're not really keeping too much track of them. Alright, 3 strontiums, 2 phosphates, I kind of keep them parallel to each other because that makes it easier to balance. 1 chlorine and 1 lithium. Alright, let's see. Strontium 1 and 3 means I'm going to need 3 strontium chlorides. So good, I have 3 of those, but look what I've done. Now I have 6 chlorines. That's fine. Let's balance that next. I have 6 chlorines, 1 chlorine. That means I'm going to need 6 of these lithium chlorides. Good. But that also adjusts this. Now I have 6 lithiums. Fine. I'll go back in over here. I'll put in 2 lithium phosphates. That means that I have 6 lithiums, but it also means I have 2 phosphates. What'd I tell you? Phosphate balanced itself. Excellent. 3 and 3, 6 and 6, 6 and 6, 2 and 2. This is the set of coefficients that give us the ratio of each of the species to each other when these two substances react to form these two substances as products.